Good morning, everybody. Welcome to a sunny Tuesday morning of Chem 1105 with your host, me, Dr. White. Hi, we got a busy day today, so I better get started. Today, I'm going to change things a little. Normally, I do the lab at the end, but I thought I'd do the lab first. Then we'll go back and do material from chapter 3. Let me remind you, tomorrow I will go through the practice problems for Appendix A2 and A4. Again, tomorrow I'll go through the practice problems for A2 and A4. I highly recommend you do the practice problems first. By the way, after test 1, you'll find out why I call them practice problems. Shh, don't tell anybody. All right, first of all, let me open up Blackboard. And let's get to my course. And if you notice on the left where it says assignments, I'll click on that. In fact, let me get the student view. Click on assignments, and you'll see today's lab, scientific method. Now, you need to download the scientific method ADA.pdf file. This is what you'll be doing. We're going to go through that. Next, you'll be filling out the questions in Scientific Method Q doc, which is a MS Word document, or PDF file, your choice. Now, I have here Introduction to Graphing, because you have to graph something. If you don't, relax. If you don't know how to graph, or if you don't know how to graph with Excel, see me either after class, come to my office hour, or make arrangements for us to meet on Zoom. And I'll show you how to do that. It's not that hard once somebody shows you how to do it. And as always, I have instructions how to take pictures if you don't have a scanner of your lab report, which is method Q. Q stands for questions. And, oh, excuse me. And I have Cam Scammer, which is a nice app to do that, but get the free version, don't spend money. Now, for this lab and all labs now, be sure to include a selfie. It should be a selfie. I'll have to change that, of you with a chemical or piece of equipment for the lab, for this lab, or you'll get 0 points. That's departmental. Now I have here answer questions 2 through 8, and after question after table 2, I'm going to change that to this 2 through 6. All right, let's look at today's lab. And it's cleverly named Faster Plop Plop Fizz Fizz. That comes from the Alka-Seltzer commercial, but it's a scientific method investigation. And here we have the overview and outcomes you can read. Here's the equipment, some of it you'll need. Now, in your Carolina kit, the box they send you, and actually, we've tried since the pandemic other kits. This one's really good. Excuse me. We used it for the first time last semester, And it really surprised me how good it worked, and the students liked it. Now, in your kit, you'll have rubber gloves, you'll have safety goggles, and they give you a good pair. Some of the kits I've seen give you a really cheap garbage, just a good pair. Now, hold on one second. I'm back. You might ask, Dr. White, how come you haven't taken it out of here yet? Because I have a better pair that I use when we've been teaching face to face. But anytime you do experiments in this lab, you should have safety goggles on. I'll say it again. Anytime you're doing an experiment with this lab or this chem kit, you should have safety goggles on. Also, wear gloves. Now, I don't have here, it's in the other room. I didn't bring it. They give you an apron. For this lab, you don't need an apron, but some of them I'd wear. Now, for today's lab, you'll have this packet with Alka-Seltzer in it. You look in your lab kit, you'll see a container like this. If you open it up carefully, you'll see a cute little thermometer. Isn't that cute? And this is in degrees C. And how do you read a thermometer? You look where the red line ends up and you line it up. And each line between 20 and 30 is 1 degree. Now, you should be able to get to 3 significant figures. So if it's in between the 20 and 21 line here, that'd be 21.5. If it's at the line between the first and second line after 20, that if it's right on the line, then it would be 21.0, 3 significant figures. Now, you have this little red thing here on yours, and that stops it from sliding off. But I'd still put this on a paper towel because you don't want to drop it. Now, another thing about lab thermometers, unlike the old medical glass thermometers that you have to shake down, you don't shake this down. You just put it in there, wait about a minute, look at the temperature. And when you're done today, make sure you'll put it back in here. I'm trying to remember, do we use it again? I think so, but, and close it. Now, you'll also need these plastic cups and this plastic beaker. Now, one of the things they ask you to do is measure volume. And if you notice on the beaker here, they're numbers. And it goes 50, 100, 150, 200. And you'll put water in here to measure the amount of water you'll need. And try and be approximately where they tell you. You also are given a grease pencil. And you can mark your cups, the marking you need to put on there. So let's talk about today's lab. That's not it. All right, now I'll let you read the background, but this lab is to teach you what's called the scientific method. And the method involves doing experiments and making observations. And this allows you to answer a question about something you observed, or in my case, when I worked in the chemical industry, One of the important things using scientific method was to solve difficult plant problems. And one plant company actually hired me because of my reputation as a plant problem solver. They were trying to close one production plant and move all the products they made at this plant over to a newer plant, a bigger one. And they were having problem with their biggest product that they could make successfully here in the old plant, but had problems in the new plant. And they had been working on it like 6 months, couldn't solve it. And their biggest customer, General Motors, we're talking about millions of dollars. I think it was 60, $70 million at risk if they couldn't move it. That's a lot of money. And you don't want your biggest customer and other customers mad at you because you can't make it here, but you can't make it there. And I solved the problem. They hired me and I made myself a outstanding reputation at that company because nobody else could solve it. How did I do it? I followed the scientific method. What is that? Well, here you're trying to answer a question. You form a hypothesis that you think here's explaining what's happening. And you design experiments to test that. You run the experiments, you analyze the data, you see if it supports your hypothesis, and if it does, you're done. And you use that knowledge to solve problems or do what you're trying to do. Now, when you're doing a scientific method, doing an investigation, you have what are called variables. And variables are factors that can be changed. Now, here's something important. In designing a scientific experiment, only one variable is changed at a given time. When you're doing a scientific experiment, you only change one variable at a time. I was lucky enough, I had a great mentor when I got into, well, in grad school, but also when I started in the chemical industry, Sid Shapiro, I think godsend, God rest his soul, he died a while ago. He was way older than I was when I started at CHEMI. And I was a fresh PhD right out of academics and first industrial job. And somehow we became friends and he became my mentor. And he taught me two things, change a couple things. Make sure you only change one variable at a time. Because if you change more than one and something's different, how do you know what made it different? You don't. The other thing Sid taught me that I'll teach you, that is common sense is not common. You say, oh, everybody should know that, or you realize that should be done. Nope. One other important problem was they had spent many months on, and they asked me to come in and solve it, and they weren't using common sense. And the last one is never assume anything, because I apologize for language. If you assume, you become the first three letters of assume, you get burned. And only once did I get burned. I've never, ever again assumed anything. All right. So we have these variables. Now, there are different types of variables. One is an independent variable. And this is a variable that can be measured and is often controlled. Temperature, concentration, time, those are all independent variables, or can be. Dependent variables are also measured, but they're dependent on the independent. You have something, you let it go longer and longer, the time changes, this changes. Now they have something called the third type control variables, and those are the other factors that you try and keep the same. Example would be if you're running a reaction in water. A control variable is the amount of water you keep the same, 100 milliliters. You don't have one with 50, one 100, one 200. And from that, you can come up with a hypothesis. Now, in today's lab, you'll need this material, which I've already shown you. And what you're trying to find out is what affects how long it takes for the Alka-Seltzer tablet to disappear. Now, what you're going to do is label 3 cups, C for cold, H for hot, and RT for room temperature, using your pencil. Next, you'll need a timing device, your cell phone, or if you have a stopwatch. You'll make what's called an ice bath. In a separate container, put in at least 300 milliliters, measure it with this, of water, use your tap water, and put in ice cubes. I think you all have access to ice cubes. If not, take one of these and put it in the freezer with some water, with some foil or something on top so it doesn't spill. And then when it comes out ice, break it up with the hammer or whatever you have. A rolling pin would be better. Now, put the ice in with the water, and then next thing you'll open up the Alka-Seltzer packages with a scissors or knife, carefully score it and break them in half. And here's a tip how to do that. Now, you take the 250 milliliter beaker and measure 200 milliliters of tap water and pour it into the beaker labeled room temperature. And then you'll turn your water from your sink to hot. When it's hot, you'll measure out 200 milliliters of water and you'll put it in a cup that's labeled H. And finally, from the ice water mixture, you'll pour it into here, measure 200 milliliters, and pour it into the cup labeled cold, C. Now, here's what you're going to do. What they don't tell you, I don't see it here. Before you start, in each cup, before you do one, measure the temperature. Put the thermometer in here, wait about a minute or so, and record the temperature. You don't take it out, you have to leave it in. Next, with your stopwatch or clock, cell phone timer ready, put half a tablet in, start, and then measure until the tablet is gone. And then you'll repeat that with the beaker, with the cold water and with the hot water. Again, measure the temperature, put the tablet in, time it until it's gone. Now, when you're done with each run, you can just dump the contents down your sink. It's safe. And if you look in table 1 data, run 1, what's temperature to cold water, and what's the time until it disappears. Remember, you're using half a tablet. and if you want any observations. Now, in chemistry and science in general, but in chemistry, you never do experiment one time. Because what if you messed up? And you usually do it in duplicate at least, but usually triplicate is a good thing. And triplicate means you do it 3 times. And you'll do after each run, like for cold water, you'll do it once. You'll repeat it again with fresh cold water and fresh half tablet twice, and then 3 times. Now here they have AVG as average. How do you do that? You add run 1 cold water time, run 2, run 3, add it, divide by 3, and that's the number you put there. Same thing with the temperature. It's not going to be exactly the same. Now they have here state a hypothesis and develop a new based on your, and you can fill this out. Now they have a second activity, and here I'll ask you, I've just changed my mind. Yeah, Dr. White. Just do one test in triplicate where you change one independent variable other than the temperature. If you have trouble with figuring that out, see me. And I've changed my mind. Let's answer all the questions. And that's today's lab, what you'll be doing. Now, if we look at the scientific method of scientific investigation, method Q, you put your name and date. Here's your data. Here are the questions you have to graph this. And graphing, you'll do the average. You'll have on the x-axis time and on the y-axis temperature. And you'll have a graph. And you'll have your independent variable on the x-axis and your dependent variable on the y, temperature. And you'll get 3 lines, I don't know what the dots are, and you can draw a line through them. And what you'll be asked to do is, at a certain temperature, say this, which you didn't use, how long will it take for the half a tablet to do that? And what you do is from your graph, you come out here, and here's where it intersects the line on the y-axis. Then you come down here, and here's where it intersects the x, and that will tell you what would be the time that it would take at that new temperature. Now, in the assignment area for this lab, they have a PDF file how to graph. Now, there are 2 ways you can graph. One, you can go on the internet and find where you can download and print graph paper. And you do it the old-fashioned way. Take a line, put it on the graph paper, put your points, draw your line with a ruler. Or you can do it in Excel. Now, if you haven't done graphing before and you need help, what do? You come and see Dr. White. Come to my office hours or come after class if I have time, or we'll set up a special meeting if you really need help then, and I'll show you how to do either way. Now, how do you find graph paper on the internet? Go to your favorite search engine, type in graph paper, notice it says graph paper printable, and I'll just do the first hit. And let's try the 1/4 inch. And you see here where it says print, and here it is, and it opens up to my printer, or you can save it as a PDF file, which I'll do right now. And this is what it looks like. Now you can also get graph paper, smaller squares. I don't know which one is the best, but that's how you do it if you want to do graph paper. You want to use Excel, see me and I'll show you. And you'll answer these questions. I've just changed my mind. For table 2, you only have to do one type of manipulated variable, not 3. Do the average and answer this question. I've changed my mind. It rarely happens, but it just did. When you fill this out, if you don't have a printer, you can write this on a piece of paper and then you can make it into a PDF file with the instructions I have. Right here. And then by next Tuesday, you need to upload this to the scientific method lab here in the assignment. Click on here. Notice the due date. Click on Browse Local Files. Find your PDF file, click, and then down here, Submit. Again, click on that assignment. Don't forget, you should also upload a selfie of you with a piece of equipment or, one of the packages of Alka-Seltzer or a plastic cup or your thermometer. And so you'll upload 2 files. One, your lab report as a PDF file, and 2, your selfie, and then hit submit. Boy, this lab work is thirsty work. And with that, we're done with the lab. That's how you do the lab. Any questions? Looking at the chat. And with that, let me close something. Let me open up something else. All right, let me check. This is what you're saying. It is. All right, let's go back to chapter 3. Remember, tomorrow I will go through Appendix A2 and A4. All right, now we were talking about, let me just move this, about where are the electrons in an atom of an element. Remember, an atom is the smallest particle of an element with all the characteristics of that element. And quick review. We have subatomic particles. Those are the particles that make up an atom of an element. And those are the electrons with a negative charge, protons, positive charge, neutrons, no charge. And the nucleus contains only the protons and neutrons. And remember, the atomic number equals number of protons. And since all atoms of an element have a zero net charge, if protons are plus charge, to get that happening a zero net charge, therefore the atomic number equals the number of electrons. Now, where are the electrons? Well, they're not in the nucleus. That's protons and neutrons. They're around the nucleus of an atom. And they are in the electron shell. And the electron shell has a region of space around about the nucleus that contains electrons that have approximately the same energy and spend most of their time approximately the same distance from the nucleus. Now, each shell, electron shell, has subshells, electronic subshells. And that's the region of space within an electron shell that contains electrons that have the same energy and are approximately the same distance from the nucleus. Now, the electron shells, time for Dr. White to be subtle. And know this. Now, electron shells have very fancy names. And the first shell is 1. Second shell is 2. Next one is 3. Last one is 4. Now, in shell 1, it only has 1 subshell. Shell 2 has 2 subshells. Shell 3 has 3 subshells. And shell 4 has 4 subshells. Hold on, I gotta get that finger fixed. But anyways, important thing that you need to know. In this table, shell 1 is the lowest energy shell. The shells have different electrons in them have different energy. And shell 1 is the lowest. And when you go down the table, the energy of the electrons in that shell increases. And shell 4 is the highest energy on that table. Now, as I mentioned yesterday, I have cut down, not eliminated, the amount of memorization for this class because I want to test you on your knowledge of chemistry, not test you on your knowledge of chemistry and your memory. Those are 2 separate things. And because of that, if you look on your screen right now, it will say important information, test number 1. At the end of the questions on test number 1, you'll see this page. And it has on there the formulas for temperature conversion. Oh, look, it's the electron shell table, just like I just went through. The only thing it does not have is the energy here. This is lowest energy. This is highest. That you have to remember. But in the past, students would have to memorize this table. You do not. Now, the subshells have letter designations S, P, D, and F. And S is the lowest energy, F is the highest. It goes increasing energy. Another way of saying it is this. This is the lowest. This is the highest energy. And remember, this symbol means less than. Now, I'm never going to ask on a test what do the letters stand for, but from atomic spectra, which we talked about yesterday, there were different lines for certain elements, and somehow somebody came up with the energy for the S subshell we call sharp. P stands for principal, and D stands for diffuse, and F stands for fundamental. How they came up with that, I have no idea. This is not my area. This is more physical chemistry. I'm an organic chemist, but I do know this stuff. Now, once again, it's time for Dr. White to get subtle. And this really should be all right. Now, when we come to the subshells, S, P, D, and F, S can only have maximum of 2 electrons. P, 6 electrons. D, 10 electrons. F, 14 electrons. And once again, like the other table, S is the lowest energy, which I had up before right here. But you should remember, as you go down the table, the electrons in that subshell are higher energy. S is the lowest, F is the highest. Now, as in keeping with lowering the amount of memorization, you'll see important information. Test number 1, this will be the last page on your test, test number 1, and you'll see I have number of electrons, and I'm going to modify this to that. And you don't have to memorize S subshell 2 electrons, P subshell 6, max D10, F14. I'll give it to you, but you still have to remember that S electrons in this S subshell have the lowest energy. And then as you go down the table, the energy of the electrons in that subshell increase. So S is the lowest, F is the highest. In the past, you'd also have to memorize this, but don't tell anybody I'm being nice. Shh. But I'll be giving this to you. Now, I'm going to turn the switch click to the off position the next couple of slides. When I do this, switch is off, click, hear that? Click. I want to go over some information I think you should know about, but this will not be on a test or on my final. Now, when it comes to where the electrons are, there's also something called orbitals. And orbitals are a region in an atom where there is the highest probability of finding a certain electron. What does that mean? Well, if I were all powerful, that would be nice, be dangerous, but nice. And I said, everything in the universe stops moving. Everything stops moving, including the electrons around an atom. And the orbital is the area in space around the nucleus where you would find the highest probability of that specific electron. Electrons are moving around. Now, if you look at cartoons and everything, see electrons moving around the nucleus like planets around the sun. Nope, 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 no. That's not the way it really is. They're in orbitals and they zoom around whatever. Now, switch is still off. Different subshell orbitals have different shapes. And I just want to talk about two important ones. The s orbital for s subshell electrons is a sphere. If I stopped moving electrons in that s orbital, it'd be somewhere in that sphere. P orbital electrons looks like an hourglass. And if I stopped the electron, it could have been there, it could have been there, it could have been there, but it's not going to be over here. And the S and P orbitals shapes have profound effects of things in our daily life. Like what? Like the shape of your hormones. That's important. Like the shape and how they interact of your RNA and DNA. Really? Yep. So orbital shapes play an important role in how things exist and their physical properties. One example, which we won't really get into this semester, is the p orbital on carbon has profound effect on the fats and oils you consume, vegetable oils and animal fats. And if you've been following the last couple of years, number of years, medical science has found what's called trans fats are more harmful for you than cis fats. And that difference is caused by the p orbitals in a fat or oil. Yep. Oh, wait. I look at the clock. It's time for a break. So let's take about a 5-minute break. I can get up and stretch, and I'll see you in a little while. Let's get going again. Welcome back. Now, we're talking about the orbitals and where the electrons are. And again, click switches off. Now, when we talk about where are the electrons, there are different ways of thinking about this. And electron, this is important. You should remember, and I'll remind you, the electron subshells are filled in order of increasing energy. You put electrons in the lowest energy, and then you go from there and fill the other ones. Now here we talk about orbitals. So for this second bullet, switches off, electrons occupy orbitals of a subshell such that each orbital acquires one orbital before any orbitals acquire a second one. And that's called the bus seat rule. Why the bus seat rule? Well, if you get on a bus and you know no one on that bus, you look around and you look for an empty seat. And only when all the seats have one person, assuming it's a bus that has seats for two people, then you'll double up. And that's the same thing with electrons in orbitals. Remember, for orbitals, anything I talk about, switches, click off. Now, again, switches off, but no more than 2 electrons can exist in an orbital, and there are different amounts of orbitals in different subshells. Now, switches on. Settle time. There are 2 different ways in chemistry of showing where are the electrons. Now, in the center, you have the nucleus with protons and neutrons, but the important thing are the electrons. Dr. White loves playing with electrons, and I have. That's called chemical reaction, because making new things, you're working with the electrons of an element, of an atom. Ooh, and it's fun too. Now, the electron configuration is a statement of how many electrons an atom has in each of its subshells. I will never, ever ask you what's the definition of electron configuration, but I will expect you to know how to do it for elements. So let's look at the following. First of all, I have here hint, numbers and letters only. Ooh, see board for examples. I have to get to work. All right, why isn't it? Sometime in the future, like soon, if you see on a piece of paper that you print out or on the PDF file, a question, 3 points each. Draw the electron configuration for, and one of them is lithium. Well, how do you do that? Well, electron configuration is for all of the electrons in an atom. Well, lithium has a chemical symbol Li. You don't have to use that, but I'm showing it to you. But what you need to do is go to your periodic table and look at lithium here, this alkali metal right here. In the upper corner, the atomic number is 3. The atomic number is the number of electrons in that atom of that element. So lithium has 3 electrons. So I'm going to write it down like this. This tells me I have 3 electrons. Now, how do we do this? Well, remember, you always start putting in electrons in the lowest energy shell and subshell. And if you look here, the lowest energy shell is 1, and it only has 1 subshell, S. So, S subshells, I can only put 2 electrons in. So if we go back to here, the first subshell is 1s. Now, there's something I should note. Hang in there. And once again, Dr. White's being subtle. When we talk about a subshell of an electron is always designated with a number and a letter. So the first subshell of lithium is not S, it's 1s. The first subshell of lithium is not S, it's 1s. A number and a letter. Now, the electron configuration, where are the electrons? And any s orbital can only take 2 electrons. Well, I need 3, so I'll put 2 there. So that tells me subshell 1s has its 2 electrons, but I need to get the 3. Now, if we look at shell 1, it only has 1 subshell. I filled it up because S1s, any S can only take 2 electrons, and I need to account for 3. So what do? Well, I filled up shell 1. I'll now go to shell 2. Shell 2 has 2 subshells. You always start filling electrons at the lowest energy, and that would be the S subshell of 2 or 2s. So we now have to go to the next shell, lowest energy, because we filled up 1s and 1, and that's 2s. And how many electrons do we need to put in there? 3 minus 2 equals 1 electron. And this is your answer. How do you do electron configuration? You look at how many electrons you need. How do you do that? You go to the periodic table, find that element, lithium. You look in the upper corner and you say, oh, it has 3 electrons. And you say, all right, I have 3 electrons. Well, I'm going to put them in shells and subshells. And from the electron shell, you always fill the lowest energy shell first before you go down this table. And the lowest energy when you start out is shell 1, and it has only 1 subshell. And you fill the subshells the same way. The 1s, you start at the lowest energy, and it's going to be S, and you can put a maximum of 2 electrons. We need 3, so I put in my 2 electrons. How did I do that? 5, 1s. Remember, all subshells of an electron configuration I should have there is designated with a number and a letter. Now, I can put in maximum of 2. I do. Now, shell 1 has only 1 subshell, 1s. I have that written, subshell of an atom. Really, this should be atom. Subshell of an atom is designated with a number and a letter. Whoops. Well, anyways, now we've done 2 electrons. We still have 1 more. 1 only has 1 subshell, which I can put 2 electrons in. I filled it. Now I have to go to the next lowest energy shell and subshell. We filled up shell 1. We go to shell 2. 2 has 2 subshells. They are S and P. You start from the lowest energy, and then you fill that up, and then you go to next lowest. S is always the lowest, then P, then D, then F. Now, remember, a subshell is a number and a letter. We're talking about S subshell in shell 2, which is called 2s. So I write it down, how many electrons? Well, I'm trying to get the 3 total. So I already have 2. So 3 minus 2 is 1. I put that in there and I'm done. All right, let's do another one. And let's do oxygen. So the question is, draw the electron configuration for oxygen. Well, in order to do that, we have to find out how many electrons does oxygen have. And the chemical symbol, which you should know, which you should know, oxygen is O. Well, we have to find out how many electrons there are in oxygen. Go to your favorite periodic friendly neighborhood periodic table. Oxygen in column 6. O, look in the upper corner, has atomic number of 8. The atomic number tells you how many electrons and protons. Well, we're only interested in the electrons, so oxygen has 8 electrons. So I'm going to write this down here so I don't forget. And by the way, I found through all the years I've been taking tests, the more I let the paper do the thinking, the better my score has been in trying to keep everything in your head. And this is a way of letting the paper do your thinking, because you write it down. How many electrons do I have to? We wrote it down. Now, you start with the first shell. lowest energy is 1, and the subshell is S. How do you know that? Wrong thing. Right thing. You always fill the lowest energy shell and the subshell in that lowest energy shell. Shell 1 has one subshell, and that's 1s. And 1s, you can put only 2 electrons in. So I'm going to put my 2 electrons, and it's subscript. Well, 8 minus 2 equals 6. I've got more to go. Well, shell 1 only has one subshell, 1s, and you can only put 2 electrons. Well, I filled that shell and subshell up. Now I have to go to the next lowest energy shell. That's 2. And 2 has 2 subshells. The first subshell, 2s, that I can put 2 electrons in. The second subshell is 2p, and I can put 6 electrons in there. So you always fill the lowest subshell, and on shell 2, that lowest subshell, remember a subshell is a numbered letter of a shell, would be 2s. I need 6, but I can only in any S subshell put 2 electrons. Well, I've done that. Now I have 4 spoken for, and 8 minus 4, I have 4 more electrons. Well, I can't put any more electrons in subshell 2s. So what do? Shell 2 has 2 subshells. The second subshell is 2p, and I can put a maximum of 6. So I'll now write the second subshell of shell 2, say that 5 times quickly, 2p. How many electrons do I have left to go? 4. What's the maximum I can put in a p orbital? 6. So I'll put in 4. And now look at 2 plus 2 plus 4. That's 8 electrons. That's what I'm trying to do. I'm done. So the electron configuration for oxygen atom is 1s2, 2s2, 2p4. Let's do one more. Oh, let's do magnesium. Now let's go back. First of all, you should know magnesium has a atomic symbol Mg. And we need to know how many electrons. If we look on the periodic table, you'll see right here, Mg in column 2 has atomic number 12. That's number of electrons and protons. We're interested in electrons. And it's got 12 electrons. So I'm going to write that down because I like to let the paper do my thinking. We have 12 electrons we have to deal with. Now, you fill the first shell and subshell. That's 1s. In case you forgot, you fill the lowest energy shell and subshell. Shell 1 has only one subshell, and that lowest energy is 1s. And you can only put, guess what? 2 electrons. So I will. Now, 12 minus 2 is still 10. I've got more to go. Now, I can only have one subshell in shell 1, that's 1s, and you can only do 2 electrons. So I filled that up. Now I have to go to the next lowest shell, that's 2. Wrong one. Right one. And 2 has 2 subshells. 2s, which I can put 2 electrons, and 2p, I can put 6. You always fill the lowest energy subshell first. In this case, that would be 2s. And I can only put 2 electrons. Well, 2 plus 2 is 4. I've got more electrons to go. Now, shell 2, as I just showed you, has 2 subshells. 2s is the lowest, and the next is 2p. Now, how many electrons can I do in 2p maximum? And remember, you'll be given this table. The past students have to memorize this, you don't. And here, that's 6 electrons. That's Dr. White. So if we look here, we'll put in we've got 12 minus 4 equals 8 more electrons to go, but 2p, I can only put a maximum of 6. Well, now I have 2 plus 2 plus 6, that's 10, but I have 12 electrons I have to go, fill or count for, and I still have 2 more to do. What do I do? Well, shell 2 has only 2 subshells. And those subshells are 2s, which I can put 2 electrons I did, 2p, I can put 6 electrons. So I filled up all the subshells in shell 2. So that means I now have to go down the table, next lowest energy, this shell 3. Now, shell 3 has 3 subshells, but you always fill the lowest energy subshell first. In that case, it's going to be S always. And I can do maximum of 2 electrons. So what does that mean? I go to shell 3 now because I filled up shell 2 with its 2 subshells. And the first lowest energy subshell in 3, remember, a subshell of an atom is designated by a number and a letter. I better do that. So the next subshell is 3s. I need to do 2 more electrons. The maximum number of electrons I can put in any s subshell is 2. And let's look at this. 2 plus 2 plus 6 plus 2 equals 12. I need to do 12, and here's our answer. 1s2, 2s2, 2p6, 3s2. Now, if you go look in your book or online, when you get to some of the higher elements, those rules break down somewhat. Notice break down somewhat. And now you got to memorize this. And I'd rather you memorize or learn other things than the exceptions. Keep this secret. Now it's time for a gift from Dr. White. A little gift, but a nice gift. Now, for my test number 1 and the final, let me get up the periodic table. I will only ask you to know how to do electron configurations up to magnesium 12. So that's all you have to do. And by doing that, you don't have to memorize any, this is different, this, you fill this instead of that. Nope, just what I just taught you holds from hydrogen through magnesium 1 through 12. And those are the only ones I'll ask on a test. So that's my little gift to you. Shh, keep it a secret. I don't want people to know I'm being nice. I don't want to ruin my image around here. I think people think I'm mean and nasty and I beat on my students. No, I don't. But that's how you do electron configuration. Now, let's move on. Now, on this slide, click, I've turned the switch. Will it be on test or final? It won't. I even wrote this right here, so you can see it on your screen. Now, there's another way of showing electrons, and that's called the orbital diagram. And it's a statement of how many electrons an atom has in each of its orbitals. An orbital is something you can have 2 electrons. S subshells has 1 orbital. 2 divided by 2 means 1. And P, which you can put in 6 NDP subshell like 2P, you divide 2 into 6, 3. Each orbital is 3. 2P has 3 orbitals. That won't be on a test or a final mark. And you show this by numbers, letters, and boxes. All right, let's move on. Switch is on full time. Let's talk about valence electrons. These are the most important electrons in Dr. White's mind in an atom. And you should know, oops, I better be subtle again. And you should know what is a valence electron. And a valence electron, those are the electrons in the outermost energy level, the outermost electrons of an element. You have different shells. Remember, shell is electrons that have approximately the same distance and same energy from the nucleus. And that means the valence electrons are always in the outside of an atom, the outermost electrons. You should know the electrons in the outermost levels are the valence electrons. In other words, they're the electrons in the outermost energy levels. Now, it turns out the group numbers at the top of the column of the periodic table are equal to the number of valence electrons of each element in this column. If you notice, I even wrote, I didn't put hints. Know this. I'll put a couple more of these. You should know, 1, what is the definition of a valence electron? Those are the electrons in the outermost energy levels, or you can also say the outermost electrons of an element. And you should know, how do I find the number of valence electrons in an element? The group numbers, the numbers at the top of the column of the periodic table, are equal to the number of valence electrons in each element in that column. Know this. Now, a couple of generalizations that I'll never ask you, but you should be familiar with. We talk about valence electrons, the representative atoms in a group, in other words, a column of the periodic table, and I'll show you this in a second, have the same number of valence electrons. Now, this is important. Now we'll go through this. The number of valence electrons for a representative element in a group, that column, is the same as the Roman numeral, or since a couple of years ago I learned, guess what? They're not teaching Roman numerals in school. When I was in second grade or third, that's when I learned Roman numerals. Yeah, but on my periodic table I give you, I have written down the standard numeral or numeric periodic group table number. Now, this is important. The maximum number of valence electrons for any element is 8. You can't have 9. You find a way, an element that has 9 or 8, more than 8 valence electrons will be rich beyond Dr. White's wildest dreams. When I say wildest, I mean wildest. That's beyond my own island in the South Pacific, my own fleet of fighter jets for me to play with, and my own Lamborghini and Ferrari. Beyond that. Why? Because it doesn't exist. Maximum number of valence electrons is 8. Oh, look. It's valence electron practice time. Well, let's have some practice time. So the question is, how many valence electrons are in hydrogen? Well, how do you do that? Well, you have to know the chemical symbol of hydrogen is H. You don't have to write it down, but you have to know it. Then you go to your friendly neighborhood periodic table and you look at hydrogen, H. You look at the top, I, or the number 1, and that tells you how many valence electrons, the outermost electrons, are in hydrogen, and that's 1. So to answer that problem, the answer is 1. Now, if I do lithium, remember the chemical symbol is Li. And I look at lithium, and it's in the same column. And you look at the top, and you see the numeric number 1, or before the A, Roman numeral 1. That means lithium has 1 valence electron. And what that also means is what I just mentioned. All the elements in the same column, up and down, have the same number of valence electrons. Lithium has 1, hydrogen has 1, sodium Na1, potassium has 1, and you go down to rubidium, and cesium and francium, which you don't have to know, but those also have 1 valence electron. And the answer here is 1. Oh, let's do another one. My favorite, carbon. And the question is, how many valence electrons are in carbon? Well, what's the chemical symbol for carbon? And you should know the letter C. And you'll be given this periodic table for test 1, 2, 3, 4, and the final. And we look for carbon, and in column 4, C, carbon. Now, we want the valence electrons. That's not the atomic number. The atomic number shows me all the electrons. Carbon has 6, but the valence electrons, the outermost electrons, you look at the top. Now, most people nowadays, students don't know IV is Roman numeral for 4. So that's why I have it written. I wrote it one way and I wrote it a little clearer the second way, 4. So that means carbon has 4 valence electrons. And you'd write that down. You get your 2 points. Oh, let you try one. And how many valence electrons does neon have? I'm going to help you out. I won't do this on a test. Chemical symbols Ne. Here's the periodic table. And why don't you figure out how many valence electrons neon has? And when you're done, give me a thumbs up or let me know by chat. And time's up. Neon is the noble gas, Ne, and it's the last column with the 8 on top. VII is 8, and I also have written the number 8. And therefore, neon has 8 valence electrons. Remember, the number in the box are all electrons in neon 10. That's not what we're asking for. We're asking for valence electrons, which are the outermost electrons, and that would be the number at the top of the column, 8. So neon has 8 valence electrons. Remember, the maximum amount of valence electrons is 8, and that's what the noble gases have. And remember, every element in a column has the same number of valence electrons. If any neon has 8 valence electrons, Ar, argon, guess what? Yep, it has 8 valence electrons. And krypton also 8 valence electrons. Now, there's one exception, and that's helium. Even though it says 8, it only has 2 electrons. So you can't have 8 valence, but that's the one exception, and we'll talk more about that at a later date. So we've done our valence electrons. And if you look in the I don't know if you can all see it. You should be able to. You look at the lower end of the page, you see I'm on page 28 of 28. Guess what? We finished chapter 3. And I believe, let's check. You see on your screen I have my syllabus tentative outline. And if you notice, next week is test number 1, and it will cover chapter 1, appendix A2 and A4, and chapter 3. And we've covered all that material now. Now, one of the things I try and do is always finish up material that will be on a test a couple of classes before that test. That gives you time to study and practice this. Remember, on tomorrow, I will go through the practice problems for Appendix 2A and 4A. On Monday next week, I will go through the Chapter 3 practice problems. And you should do these. First of all, you're not going to learn chemistry the night before a test. To do well in my test, do the practice problems. Also, if you're not in lecture with me, watch my videos. And I looked, let's look again. If you notice, there are a lot of views. You people are watching it. Yesterday, I put in yesterday's lecture, which I'm smiling. Hey, and you see already 5 people have watched it. And since we only have 24 people in the class, this semester you've been watching the videos. Don't just watch them. Do the practice problems on your own. Now, if I look at the clock, let's take a 5-minute break. We'll come back, do a little more. I'm really ahead of schedule, so we'll end a little early, but I want to spend a few more minutes on chapter 4, because that's what it says in my syllabus, and I'll see you in 5 minutes. Okay, let's take a 5-minute break, and I'll be back after I stretch. I'm back. All right. Now, we're going to start on chapter 4, but before I do that, don't forget the the safety lab we did last Tuesday is due today. Make sure you upload it. Now, for the safety lab, you don't need a selfie. All the rest of the labs you will. Don't forget, if you haven't done it already, and I sent out email to those who haven't, I need by tomorrow the distance learning DL safety contract. You need to sign it, date it, make it into a PDF file, and then upload it to the assignment area Blackboard. Almost all of you have, but I think 3 haven't. I need it by tomorrow, because by tomorrow, I have to certify by tomorrow night whether or not you're actively participating in this class. And if I've seen the safety contract, that is good enough proof you're actively participating at this point. So don't forget the lab. The lab I did today at the beginning of today's lecture is due next Tuesday. Now, listen carefully. Labs are easy points. I don't ask for a whole 20-page lab report. They're not that hard, but you have to do them and you have to turn them in. And since the pandemic, a problem I've seen with students is they don't do the labs or turn in a lot of them. Each lab is 10, I like special effects, 10 points, and I'll be serious. If you don't do 6 labs or 5 labs, that's 50 points. That can drop you a whole letter grade if you're doing good on the test and the final. So hand in labs. All right. Now, as I said earlier, I finished everything for test number 1 material. Don't forget tomorrow I'll be going through Appendix A2 and A4 problem set. And next Monday, I'll do Chapter 3 problem set. You should do them before I do. Now, I'm going to be doing Chapter 4. That won't be on Test 1, but it will be on Test 2. So let's get into that. Let me open it first. And I'm going to start out with Chapter 4, what I call Part 1. And that's chemical bonds. Now, when we talk about chemical bonds, the first thing I like to talk about is the Lewis structure. And hint, you should know this. And I'll never ask you what is the Lewis structure, but I will ask you to know how to do one. And it's named after Dr. Lewis. I don't know where he's from. Hold on one sec. Let's take a look. Who's that handsome guy? Anyways, it's also known as dot structures or Lewis dot formulas. I've never heard it. Ah, he was from University of California, Berkeley, and about 1920, he came up with that, or 1916. So anyways, Lewis structure consists of the element symbol with one dot for each valence electron. I didn't mention earlier, but valence electrons are only S and P subshell electrons, never D and F orbitals or subshells. So how do you do this? Always place one electron on each side of the element symbol before putting a second electron on any side. So let's practice Lewis structures. And let's do the Lewis structure for sodium first, then magnesium, carbon, oxygen, bromine, and argon. Ooh, we got a lot to do. Let's see if this works. It did. All right. And sometime in the future, you see it on a piece of paper, test 2 maybe. Remember, this is test 2 material, not test 1. So the question is, draw the Lewis structure for each 1 or 4, and A is sodium. Each one of these is 3 points each. Well, how do I do that? Well, Lewis structure is only for valence electrons. And first of all, how many valence electrons does sodium have? And we go to our friendly neighborhood periodic table and see sodium Na. You want valence electrons. 11, the atomic number is all electrons. You go to the top, you see the numeric number, Roman numeral 1. So sodium has 1 valence electron. And how do you do the Lewis structure? You write the chemical symbol, and on the sides, you put a dot for a number of valence electrons. And I could do this, and 2 more I could do. And this would be an answer, so would that. Let's do carbon. And now, how do we do that? Well, we have to find how many valence electrons, the outermost electrons in carbon. And you should know the chemical symbol for carbon is C. And now I'll go to my friendly neighborhood, not Spider-Man, but periodic table. Here's carbon C. I look at the top, not the atomic number. That's not valence electron, that's all. I look and I see the number 4. Also the Roman numeral 4, but most of you have never learned Roman numerals. Sad but true. So I have 4 valence electrons to deal with. VE is my way of shorthand for valence electron. So how do you draw the Lewis structure? You draw the chemical symbol, then you put a dot on each side of that for each valence electron before you double up. So I have 1, 2, 3, 4. I'm done. Now, watch closely. You never double up until each side has 1 valence electron. You never double up until each side has 1 valence electron. So if I were to do this, This is wrong. Why? Because I have two valence electrons doubled up, and I still have room here to put a dot, a valence electron on each one. You put one on each side before you double up. You know something? I have to share the fun. And I'll let you try draw the Lewis structure for oxygen. Oxygen, I'll tell you now, has the chemical symbol O, and I'll help you out. No, not really. I'll first let you try. And the first thing you have to do is find out how many valence electrons does oxygen have. You try it, and then I'll tell you. All right. Oxygen, right here. You look at the top, not the atomic number, but the top, and you see the Roman numeral VI, which most of you don't know means 6. And I wrote down in red 6. So oxygen has 6 valence electrons. But you have to write the Lewis structure. So it's your turn. Remember, one dot on each side before you double up. And give me a thumbs up or tell me in chat when you're done. I forgot to do the poll. I'll get that tomorrow, hopefully. I remember. Don't forget, one dot on each side for each valence electron before you double up. All right, my turn. We figured out oxygen has valence electrons. You do the Lewis structure, you put the chemical symbol, and we put one dot on each side, one valence electron. A dot is a valence electron before we double up. So I'll do 1, 2, 3, 4. But I need 6. 6 minus 4. I have 2 more to go. Now, organic chemist, which I am, put the next one here and the next one here. And this is how we draw it. Now, you could have easily done, I'll put this second one, number of the 2, and this one. This would be, and for oxygen, you have 2 sides with 2 electrons and 1 side with 1 valence electron. And these, I think, would be the 4 answers. I'm always going to do this one because I'm an organic chemist, but any of these other Remember, one electron on each side before you double up. And that's how you do. Oh, let's do one more. And the question is, draw the Lewis structure for bromine. Now, you need to know bromine has a chemical symbol Br. You don't have to memorize valence electrons for the elements. You have to know how to find it on your friendly neighborhood periodic table. Bromine, Br. We look at the top here, see VII, which is also known as 7, which I have here, and therefore bromine has 7 valence electrons. Remember, this is how I draw my 7, and I'll let you do the valence Lewis structure for bromine with 7 valence electrons. Your turn. Remember, you put a dot on each side for each valence electron, and then you double up for the rest of them. You never have more than 2 valence electrons on a side. All right, let's do it. We have 7 valence electrons. We'll put 1, 2, 3, 4. Well, I got 3 more to go because 7 minus 4 equals 3. So I'll start doubling up. 5, 6, 7. And this would be one answer. Now, if you look at having 7 valence electrons, 3 sides have 2 electrons and 1 side has 1. So I could just as easily done this. And any one of these 4 would be the correct answer. Doesn't matter, they're all correct. So remember, Lewis electrons show the valence electrons for an element. You take the alchemical symbol and 1 dot on each side, and then you double up. You can't have, like I have here for carbon, wrong, because it is, a side that's doubled up when you have a side with no dots, valence electrons. And this is a skill you should have in for test number 2. Now, when we talk about chemical compounds, there's 2 types, ionic compounds, and the book calls the other type molecular. I like the name covalent chemical compounds. Now, I'm never going to ask you, but I will be using the term molecule. What's a molecule? That's a group of 2 or more atoms that function as a unit. They're held together because the atoms are tightly bound together. What would be an example of molecule? Well, the water in my water bottle is made up of water molecules, which are 2 hydrogens, 1 oxygen held together in what we call a water molecule. If you happen to go to a restaurant and order something like French fries, what do? Even though my cardiologist is you keep it low, and I do, you use sodium chloride. Molecules, and that's the sodium chloride molecule. You know that as table salt. And the white solid you shake on your French fries is made up of molecules of sodium chloride. Now notice that's NaCl. And I have to admit that if you go out with a group of chemists to breakfast, lunch, or dinner, and I have to admit, I've done this more than once, twice, or 3 times when I'm with a group like that. One of us will say, will you please pass the NaCl? NaCl, NaCl. We don't say the salt or sodium chloride. So a molecule is a group of atoms that function as a unit because they're tightly bound together. Now, what do we call that force that keeps atoms attracted together in molecules? And we call that a chemical bond. No relations to James Bond 007. Oh, that was a bad joke. I'm sorry, not really. But anyways, I'll never ask what's a chemical bond, but I'll use that term analogy. That's the attractive forces that hold atoms together in more complex units we call molecules. In water, the hydrogens and oxygen are held together by a chemical bond. In sodium chloride, the sodium and chlorine atoms, one of each, are held together by a chemical bond. Now, there are 2 types of chemical bonds, ionic and covalent. And if I look at the clock, I think this is a good time to stop because we're done for today. I've done a lot. You've done a lot with me. And so let me remind you, don't forget, last week's lab is due today. Don't forget, the lab I did today at the beginning of the lecture is due next Tuesday. Labs are easy points. You don't want to lose them. Each lab is 10 points. If you only hand in 7 out of the 13, or actually 14, I dropped the lowest. But if you're missing 5 or 4 labs, you've lost 40 or 50 easy points. That's going to hurt your grade. I don't want to see that. And I hope you don't. So hand in labs on time. Don't forget, tonight, Tuesday, and also tomorrow, Wednesday night, from 6 to 7:15, I have my office hours on Zoom. Come on by, say hello, and if you need help, I will. Also, if you have questions, remember in my class, there's no such thing as a dumb question in my world too. What do? You can email me, or if you really need special help, contact me. I'll see if I can set up a Zoom time when we can both talk together. And with that, I'm done for today. Gang gesund. Goodbye.